Is good? Yep. All right. Wasn't saying anything politically incorrect before class, of course. Let us begin with a word of prayer. Dear Father, we thank you for this day and for most of these students. Help us to glorify you, what we do, Lord. In your name I pray. Amen. All right, so I promised a ring by October, and today is that day. So this is lecture 21, which is kind of funny because lecture 20 is tomorrow, I think. Well, when I say tomorrow, that's with the understanding that Tuesday and Thursday don't exist to us because those are not abstract algebra days, and as such, they don't exist. Because, of course, the only thing that matters is abstract algebra, right? I am joking. Real analysis also matters. Maybe complex, I don't know. Just kidding. I don't teach complex. Wait a minute. I don't teach real analysis. Let's throw that one out. I digress. Okay, definition. A ring, R, is a non-empty set with two binary operations known as addition and multiplication. So the addition is something like R cross R to R again, and the multiplication, which we don't usually even have a notation for, is again from R cross R to R again. These are functions. In other words, they're binary operations on the set, addition and multiplication. In fact, typically, we just use the notation A comma B under the addition map goes to A plus B, right? A comma B under the multiplication map just goes to AB. I don't know, I don't even have really names for these, but it's got addition, it's got multiplication, and we have a bunch of axioms. So 1, 2, 3, and 4 go to say that R is a abelian group with respect to the addition. So A plus B is equal to B plus A. A plus B plus C makes sense. In other words, it's associative. There exists a 0. A plus 0 is equal to A is equal to 0 plus A, right? And also, for each A in the ring, there exists minus A in the ring such that what? A plus minus A is equal to 0. So taken collectively, axioms 1, 2, 3, and 4 say that the ring is an abelian group with respect to addition. But there's more. A ring also has a multiplication, and the multiplication is first and foremost associative. So axiom 5 here is that AB times C is equal to A times BC. All right, and then here's some interlinking conditions, some distributive conditions. So A times B plus C is equal to AB plus AC. And also, we have that B plus C times A is equal to BA plus CA. Now, both of these conditions must be stated because we don't generally assume the multiplication of a ring is commutative. All right? Generally speaking, ring multiplication is not assumed to be commutative. There's also a number 7 for us. And number 7 says there exists one, or a unity, a multiplicative identity, if you like, such that 1 times A is equal to A for all A in the ring, of course. Sorry, I'm missing some qualifiers here. I mean, there should be some for alls, and there exists various places. I hope you can put those in. They're in the notes. So that's a ring. And technically speaking, what I'm looking at right now is a ring with identity. So axiom 7, depending on what you look at, may or may not be included in the definition of a ring. Furthermore, definition, if R is ring where AB is equal to BA for all A and B in the ring, then R is a commutative ring. So the commutative refers to the multiplication. Of course, we always assume that the abelian addition is abelian, right? So the addition commutes without, that's always the case for a ring. But the multiplication may or may not be commutative. Furthermore, if we take a ring and we delete axiom 7, all right, if you get everything except for axiom 7, then what do you call that? But possibly not 7, is called a RNG. So a ring, if you will, is a ring possibly without identity. Some books would just call it a ring, and then they'd say that our ring is a ring with identity. So I'm going to engage in the horrible pun, which is to delete the I to indicate that the identity has been deleted in a ring. All right. All right. So there's many examples that we could list, right? So here's some examples. Of course, the integers, Zn, polynomials. So this is polynomials. With z coefficients. Right. All rings. There's fancier examples. You could look at the function space from some set to a ring. All right, so this is just f going from the S to the ring such that f a function. How would you add two things in this function space? Why is this a ring? So let me pick a couple. Suppose we have like f and g in here. Well, how would you define f plus g? How would that be defined? How do we define addition of functions? Pointwise, right? So let's say of s is equal to f of s plus g of s, yeah? For all s and s. So here s is just some set. S itself does not have to have any kind of like additional, additive or multiplicative structure. It could be a, I don't know, it could be a set of cats, right? It could be the grades of people in this course at the end of the semester. I don't know. I mean, pick your, whatever you like. That would be a non-empty set, right? You're not all going to drop, right? No, I mean, we can say this with certainty. No one else in here is going to drop the course. We agree? All right. Some of you are not shaking your head as rigorously as I'd like, but so this will define the sum of two functions. How would we define multiplication? F times g of s is equal to f of s times g of s, all right? What's the identity? Is this a ring with identity? I mean, it is. This is a ring because I'm supposing here that R is a ring. All right? So what would the identity function be? How about this? 1 in this, I don't know, I need to come up with a name for it. Let me put a hat on it. 1 of s is equal to 1 for all s and s gives 1 hat a function from s to r, right? And you can check that 1 hat is a multiplicative identity for this ring. So this is pretty out there. You give me any ring, you give me any set. If I look at functions from that set into the ring, then this has a natural ring structure. Yeah.
Is there a reason you put 3 lines in the equality there for equals 1?
Yeah, it's identically equal to 1. So that means, but you can reduce it to 1 if you, 2 if you like. I mean, whatever. So there was, but we can retract it if it's bothersome. Okay, so what are other examples? So generally speaking, this would be a use of that notation that would be better, Liam, like this. If I say f equals 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 1, that usually means that f is identically equal to 1. So a better...
But those could be different identities.
So I could have said this, 1 hat is equal like that. That would say that 1 hat is the function which is identically equal to the constant 1 in the ring. Now, does that answer your question? In short, I probably shouldn't have put 3 equals there.
You shouldn't have?
Probably not.
Okay.
It raised this question, which was not interesting, so there you go.
That answers my question.
Okay. I mean, I don't dispute the question, and you should ask it. It's good. I'm just saying that it's my fault that it was asked. So to be clear, the blame is on me. And the Democrats. But let's see here. Let's see. Just throw that in there. But all right. So any field is a commutative ring. Right? So, for example, the reals, the complexes, the rationals, Z mod of prime, although that already fits into the Zn case. I mean, and there's fancier fields, but fields are examples of rings. A field is a special kind of ring. More about that as we go on today. Okay, guys? There's weirder examples, though. We could take R a ring and set R prime equal to say R n by n. So this is the matrix ring with entries from a ring R, right? And we would define addition of matrices and multiplication of square matrices just as we did in linear algebra. And you can check that matrix multiplication and addition satisfies all the axioms of a ring. Of course, this is a good example of a ring which is not commutative, right? Because matrix multiplication is generally not commutative. This will give us an example of a non-commutative ring. There are other non-commutative rings. For example, the quaternions, right, is also a non-commutative ring. Because what does it have? It has I times j is equal to minus j times I, right? That's a pair of elements in the quaternions which do not commute, so it's a non-commutative ring. And you can, of course, as we talked about briefly, the quaternions are actually, in fact, what's known as a skew field. They're almost a field, they don't commute. But it is the case that every non-zero element, every non-zero quaternion has a multiplicative inverse. There's another sort of overarching construction we can do. R prime is R1 cross R2 cross R3 cross dot 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 cross Rn. These are all rings. Then R prime, if you like, the Cartesian product of n rings would form the so-called product ring. This is again a ring. We just add, like we did in linear algebra, component-wise. And the multiplication in the product ring is just done component-wise. Just like the product group we looked at before, right? So like if I had x1, x2, dot 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 xn, I multiply by y1, y2, dot 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 yn, I get x1, y1, xn, yn by definition. That again is going to be a ring. What's the identity in the product ring? It would actually be the tuple of ones. It's the one from each ring altogether. This is the identity in there. In a ring, we can also talk about things we've talked about. So when you guys discuss, in the prequel 2, I think it was, I talked about, maybe prequel 1, I forget. It's been so long ago. But I talked about divisibility, right? We talk about multiples and divides by. This terminology generalizes to rings. So if I was to say A divides B for A and B in a ring, what would I mean by that? See, it's so pretty. I hate to erase it, but I must. I'm guessing, so you guys tell me, where are they in Calculus 3, given this picture? What does this picture say? What has begun? No, not there yet. Surface integral, no. This is a picture motivating the double integral. Talking about the volume bounded by the, yeah. And that's a grid of a sample. Anyway, I'll shut up. Fortunately, we don't use Calculus 3 in here much. So, all right. So A divides B for A, B, and R means what? There exists, let's say, R and R, such that what? B equals to what? R, yeah, AR, right. Now, okay, fine. At this point, I'm going to assume R is commutative at this point, all right? You could talk about divides by in a non-commutative context, but I just don't have the energy to do it in here. So when I start talking about divisibility theory, I'm going to assume that we're talking about commutative rings. Most of our examples are commutative rings. All right. So you can talk about divides by factors. What would a unit be? What's a unit? A in R, a unit. What would that mean? There exists A inverse in R such that what? A times A inverse equals to the identity, right? The multiplicative identity. So that would be a unit. There is tons of really obvious things that are true for rings, but are not part of the axioms. These can be proved from the axioms. Here's a list of them. A, B, C in the ring. We have the following. 1, 2, 3, 4, 5. First of all, A times 0 is equal to 0 times A. A times minus B is equal to minus A times B is equal to minus parentheses AB. And the first one, what else can you say? That's equal to what? What's 0 times A equal to? 0, right. 3 minus A times minus B is equal to AB. 4, A times B minus C is equal to AB minus AC. And you also have that B minus C times A is equal to BA minus CA. And finally, last but not least, 5 minus 1 times A is equal to minus A. And the product of minus 1 and minus 1 is equal to 1. I'll prove 1. So if I have A times 0, that's A times 0 plus 0 by the definition of the additive identity, which is by the distributive property A times 0 plus A times 0. Therefore what? A times 0 is equal to 0 because I can subtract a 0 from both sides. It is, after all, an additive abelian group, right? So we have cancellation property with respect to addition from day 1 in here. And there you go. A times 0 is equal to 0. And a very similar argument can be used to show what? That 0A is equal to 0. So they're both equal to 0, so they're equal to each other. That's axiom 1. Well, it's not an axiom. These are trivial results of the axioms, which we would like to use without referencing it. Like, I don't want you to have to say, by theorem 4.1.12, I can make this step in what goes forward. Oh, here. Okay, guys, I mean, these things we're going to use without explicit reference going forward. Is that okay with you guys? I hope it's okay, because otherwise it would slow us way, way down and add very little interesting to the course. Next up, subring. What is a subring? Care to guess? You guys got a test on this Friday, right? No, not on this. I'm not a monster. All right. R a ring. S is a subset of R, is a subring if what? S is a ring with respect to the addition and multiplication of R suitably restricted. All right. But there's more. S is a sub RNG of R if it is a subset how to say this, which is a ring which is an RNG with respect to the operations of R. What's that mean? That just means that it's a subset, it's closed under multiplication, it's closed under addition. The addition and multiplication satisfy axioms 1 through 6, and yet S possibly does not have the identity. All right? So let me give you an example of that before I tell you any theorem or anything. The integers are a ring, right? They have 1 is in the integers, right? Like number 1. And what's a subring? How about this? S equals to even integers, 2z. Is this closed under addition? Is the sum of even integers even? Yep. Product of even integers even? Yep. Does it satisfy all the same rules of arithmetic as the integers? Absolutely. Is this a subring? It is not under our definition because 1 is not even. Right? So this is a sub RNG of z, but not a sub ring of z. 1 is not an even integer. Now, there is a subring test. What do you think the subring test looks like? Theorem. A subset S of a ring R is a subring if it is closed under addition, multiplication, and shares the same multiplicative identity. That is much easier to write in symbols. So what I'm saying is that if we have that x and y are in S, implies that x, y, and also x plus y and 1 are in S. then S is a subring. Admittedly, the fact that X and Y are in S has little to do with the evidence that 1 is in S. It's just that that's necessary, where I'm, of course, assuming that 1 is the identity in R as well. This is the analog of the one-step subgroup test. And the proof is pretty straightforward. I'll just talk you through it. Why is this going to work? So first of all, let's see here. Oh, wait a minute. Is that right? I think I just did that wrong, guys. Oh, yeah. So sorry. You guys gotta stop me. Not addition, subtraction. Subtraction is what we want there. And this is supposed to be x minus y. All right? Because that is analogous to the one-step test, which is what? AB in the group implies what? How'd it go? Was it AB inverse was in the group? Right? So in the additive context, that becomes A minus B in the group. And that's why we want subtraction, because then with respect to the additive group structure here, we have, by the one-step subgroup test from abelian groups, that this condition gives us that S is what? A subgroup, provided it's non-empty. But we know it's non-empty because 1 is in there, right? So it's non-empty because 1 is in there, and it satisfies this condition. Therefore, by one-step test, S is a abelian subring. It's an abelian subgroup of R. And then what you have to do is you have to check that the multiplication satisfies all the appropriate axioms. But that's straightforward to do because all of the multiplications in S are also multiplications in R, and therefore are associative and satisfy the necessary distributive properties. Really, the only thing that's not clear a priori before the fact is that the product of two things in S should again be in S, but we're assuming that's true, so we get that. This is needed just to make the multiplication on S be a binary operation, to close back in on S. But anyway, that's the subring test. Of course, if you wanted to show something was a subrung, what would you do? What would be the subrung test if you wanted to think about that? So yeah, for subrung, we just need xy and x minus y are in S, which is not empty. Yeah. Once for the subrung, we need to figure out something's in there, right? Otherwise, we'd have not. We need the non-empty condition to be met somehow. But yeah, then it would just suffice to have the product and the differences in there. But we wouldn't have to have 1 is in the sub RNG. In fact, so if you guys look at Galilean, and I do mean to put a copy of that in the conference room. I keep forgetting to do it. If one of you would remind me at some point, I would do it. So you could look at it if you wanted to. I do keep referencing Galilean in these notes, and it might be convenient for you to actually be able to look at that sometimes. But in Galilean, his definition of ring does not include identity. And this leads to some really weird features. Let me show you. I say it's weird anyway. You can take it or leave it, but here's one. So, example, if we look at R equal to Z6, and we look at S equals to 2Z6, in other words, 0, 2, and 4. All right? We can make Cayley tables for the addition and multiplication in here. So let's do that. Let's just actually look at the multiplication in S. So you got your 0, you got your 2, you got your 4, right? And how does multiplication in S work? So we got 0, 0, 0, 0, 0. 2 times 2 is what? It's 4. 2 times 4 is 8, which is 2, right? So 2, 4 times 4 is what? 16, which is 4, right? And so the thing is you can check that 4 times S is equal to S times 4 is equal to S for S equals to 0 2, and 4. Right? See that? Of course, if I put s equals to 0, it works. If I put s equal to 2, 4 times 2 is 2. Yeah. If I put s equals to 4, 4 times 4 is 4 again, right? So what does this mean about 4? It is the multiplicative identity of s. What is the multiplicative identity of here, of this? What's the multiplicative identity here? It's 1, right? So a sub-RNG, a subrung, may actually be a ring, but not a subring. It's not a subring because it doesn't share the same multiplicative identity as the original ring. So I don't know about you, I find this feature slightly disconcerting that you can have a subset which has a different multiplicative identity than the larger set for which you're restricting the operations of. Yeah, this will not happen in a subring for us. This won't happen. The multiplicative identity is, by assumption, the multiplicative identity for the subset. All right. So anyway, I will try to stop talking about sub-RNGs at this point. So a few more examples in here. So next up is integral domain. What is an integral domain? R is an integral domain if R is a commutative ring with no zero divisors. So by zero divisor, I mean what? I mean AB equals to 0 with A and B not equal to 0. A zero divisor in this usage here. So, I mean, so this is what I mean by zero divisor. If you like, you could say non-zero zero divisors just to drive home the point. Right? In some sense, 0 is a divisor of 0. Right? You know why I'm saying that? We could write 0 is equal to m times 0, right? So is 0 a divisor of 0? It is with respect to the usual language of divisor, right? So when we talk about zero divisors here, we're talking about the interesting ones, non-zero zero divisors. And the thing is, for an integral domain, you got none of these. So what does that give you? Can you guys think of an example of a integral domain? Real numbers? Okay, yeah, sure. I think that would work. Can you think about something less greedy? How about integers, right? I mean, real numbers is a good answer. I'm not disputing it. But the integers are an integral domain, right? The product of two integers can only be 0 if one of those is 0. How about Zn? Is Zn an integral domain? If we have r equals to z6, for example, this is troublesome because we have 2 times 3 is equal to 0, yet 2 and 3 are not 0, right? So apparently z6 is not an integral domain. Another definition. if we have a ring, the set of units in the ring, U of R is equal to R in R such that what? R is a unit. So I probably should have defined this earlier. Sorry, I have ruined my flow. I'd have to remix this tape. Let me track. We don't do tapes anymore. We do tracks, right? Yeah. I have many examples, too many to write on the board here. I would encourage you to read these notes, all right? I have about at least 10 examples I've not written on the board, which are important for you to just think about for a minute or two. The theorem that we can prove about integral domains is that we have the cancellation property. So let's prove that. Theorem. If R is integral domain, then, and A is not equal to 0, and, and AB is equal to AC, then B equals to C. So what would be here, let me show you how not to prove it. So here's how to get this wrong on the next test if I was to ask it. Proof. I'll make it maximally wrong. How about that? So, okay, so AB equals to AC. So I'll divide by A, and it gives me B equals to C. Okay, none of you are this bad. You do something instead. Okay, let's give you more credit than that. Instead, you'd say this. Okay, so A inverse AB is equal to A inverse AC, which implies that B is equal to C. Okay. But that's almost as offensive as the first thing I wrote, because it assumes something which we're just not given. Why would A inverse exist? R is an integral domain. Who says every element of an integral domain has an inverse? Right? The group of units, in fact, this is a group, gives you all of the invertible elements. What are the units in the integers, for example? What's Uzi? It's 1 and minus 1. Those are the integers which have integer inverses. Does 2 have an inverse? Does 3 have an inverse? Does 4? You're like, yes, they do. It's a half, it's a third, it's a fourth. That's wonderful, but that's outside the universe of integers, right? So those are not inverses which exist in the ring. So I can't do what I just wrote in red. It's just not allowed, right? So how do I do it? I say, okay, so suppose that A is not equal to 0 and AB is equal to AC. Then what? Then AB minus AC is equal to 0, right? And then by the distributive property, I get what? This implies that A times B minus C is equal to 0. Okay, actually, technically, it's by the part 2 of the theorem I said I wouldn't reference. Ooh, I've almost referenced it. I'm sorry. I didn't name it by number, though. So by a theorem we can do that, right? And what's this? This is this times that equals 0. But A is not equal to 0, and R is integral domain. So what's that mean? Hence, B minus C must be the 0, right? Otherwise, we'd have 0 divisor, which is against the definition of an integral domain. So, hence B minus C is equal to 0, which is to say B equals to C. So we get cancellation without inverses in an integral domain. This is new. We had cancellation before because we had multiplication by inverse. Now we've got cancellation because we've got a distributive property and we've got addition and multiplication working together for cancellation. So there you go. Here's something, though. If you don't have the cancellation property, then you don't have an integral domain. You can look at this another way, right? This theorem is a little bit shocking to me. Each finite integral domain is a field. So, all right, so let's give it a name. Let's call it D. Suppose D is finite. Then what? And, you know, with let's suppose 1 is the identity, all right, the unity. And let's suppose that we're picking A be an element of D with what? With A not equal to 0, right? Now, if A is equal to 1, then we're done, right? So if A is equal to 1, then if A is equal to 1, then it's its own multiplicative inverse, right? So, by the way, what does it take to show it's a field? What are we trying to prove? We're trying to prove that every non-zero element has a multiplicative inverse, right? That's what it takes to prove something's a field. A field is a commutative ring in which every non-zero element has a multiplicative inverse. All right, so if A equals to 1, we're done. So suppose A is not equal to 1, right? Then A squared, A cubed, A to the 4th, dot, 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 must do what? This is a finite integral domain, right? So can that go on forever? Right? No. Eventually, one of those has to be equal to what? Was that, did you say 2? No? I don't know how I got 2, but let's say A to the K must be equal to 1 again, right? You said what? Okay. Okay. You said 11? No. Oh, okay. But it's finite, right? So this list eventually has to loop back to 1. It can't loop back to 0, right? Because I mean, 0 can't be in this list. If it was, it would give you a 0 divisor. All right, so it has to come back and hit 1 eventually. Otherwise, the list would be infinite, which would contradict the fact that this is finite, right? But then once you write that, you've got what? A times A to the K minus 1 equals to 1, which says that A inverse is A to the K minus 1, right? But that's an arbitrary element. Therefore, we've shown every non-zero element has a multiplicative inverse. So a finite integral domain is a field, right? Corollary. How about infinite? Now, this we've proved before with other arguments, but it's fun to prove this now in our current context. The corollary, if P is prime, then Z. By the way, in the infinite case, it fails, right? The integers are not a field. We already talked about that today, but they're an integral domain. So an infinite integral domain need not be a field. It might be, like the reals Bethany gave me. That's an infinite integral domain, which is also a field. right? But in the finite case, it has to be a field because of this argument. Okay, so if P is prime, then suppose we had, lost track of my, I can't flip my paper. If we have AB equals to 0 in ZP, right? Then that means that AB is equal to P times K, right? For some K in the integers, right? Which then implies, by Euclid's lemma, what? Either P divides A, or what else? Or P divides B, right? So what does that mean? In other words, either A is equal to 0, or B is equal to 0. What's that say? In Z mod P, if we have a product of residue classes, if you like, equal to 0, then either one or the other of the classes must be the 0 class. Which is to say, there are no 0 divisors in Z mod P, but Z mod P is finite, therefore it's a field. That's a kind of different argument that we found before. Before I actually described the mechanics of how we calculate inverses because that was more important to us. There it is. So I'm going to use the projector here for last minute. So the thing that's left for me to talk to you guys about is just an example or two, which will take me too long to write out. And the definition of characteristic. What's a characteristic in a ring? So the real numbers, complex numbers, rational numbers, these are fields of so-called characteristic 0. What does it mean to have characteristic 0? This means that you can add the multiplicative identity, which is 1, to itself all day long, like 1 plus 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 1. And no matter how long you add 1 to itself, you never get 0. This is a characteristic 0 field. You're like, that seems right. Well, how about in Z mod P? What's the characteristic for Z mod P? How many times do you have to add 1 to itself before you get back to 0 in Z mod P? I heard a P? We have a winner, yes. So Z mod P is a characteristic P field. And so you can have characteristic 2, characteristic 3. You can prove that the characteristic must be prime. But there are other characteristic 2 fields other than just Z mod 2. All right? In fact, in my notes here, I actually have, I think, maybe an example of a characteristic 3 field which has 9 things in it. So this is one of those places where I'd like to have a copy of Galean for you guys to look at if you want to, because this, it's funny. This example here, oh, you did it? Okay. So this example here, Z3 adjoin I, which is A plus BI, where A and B are in Z3, it's got 9 things in it. Dup, 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 dup. And in fact, if you look at the condition, you just try to see, hey, are there any 0 divisors in here? In order to have a 0 divisor, I'd have to solve both of these equations in x and y and a and b simultaneously over Z3. And if I look at that, it gives me this system of equations, which I can, what did I do there? Huh. Oh, I just multiplied by the inverse matrix to that. This is a Z3 matrix, right? So this is its inverse. I guess we could get into trouble if x squared plus y squared could be, not invertible in Z3 for a particular choice of x and y. But I think if you look at x squared plus y squared, for x and y coming from Z3, this cannot be a 3 or a 0. Like if we have x and y are both 1, we get 2. If x and y are both 2, we get what? 4 plus 4, which is 8, which is 2. That's got an inverse. If I take one of them is, 1 and one of them is 2, I get 5, which is 2. You look through all the different possibilities, there's no way this thing can be non-invertible, which means, well, actually that means that there's no, that actually is half of the proof that, let me shut up. Anyway, the point is when you do this calculation and you sort through it, you see that there in fact are no zero divisors except for a and b to be 0 itself, which means, by the way, that this is a finite set. It's got 9 things in it. It's got no zero divisors, so it's an integral domain. Consequently, by a theorem, it's a field. So here's a field with 9 elements in it, which has, by the way, characteristic 3. The multiplication table is given in Galilean. Here's a more interesting one. This is z adjoined the square root of 2, which you multiply with rational number coefficients like so. And you can prove that the conjugation, like the rationalization trick, actually serves to define a multiplicative inverse in here. Like the reciprocal of 1 over a plus b root 2, it works out to just a minus b root 2 over the difference of the squares. All right, and this actually is impossible for this to be 0 for a and b integers. So this is a field. Q adjoined the square root of 2 is a field, which is larger than the rational numbers, but not as big as the real numbers. It's a field in which you find the square root of 2, and it's got inverses to that. Anyway, here's the definition of characteristic, as I said. And you can prove that if R has characteristic, if one has additive order n, then the characteristic of R is n. And so yeah, my definition of characteristic actually is for all x in the ring, like n times x is equal to 0 for all x in the ring. But actually, when you work it out, it suffices to just show that 1 added n full times gives you back to 0. Like that, guilt by association transfers to everything else in the ring. So anyway, that's pretty much it for today. And Wednesday, what are we doing? A review. That's right. So back to lecture 20. Thanks, guys. Or 20, or 19 maybe? I don't know. I lose track now. Thanks, guys.